Welcome back, dear students. We are now in part 4 of Gravitation Chapter. So let's just quickly revise what we did in the previous lecture, part 3. We talked about the graphical representation of variation of acceleration due to gravity small g, right, with height and with depth, right. So it's maximum on the surface of Earth. As we go below the surface of Earth, as we go inside Earth, right, the value of small g decreases linearly till we reach the center of Earth, and also as we increase the height, right, go away from the center of Earth, then initially it's going to decrease linearly, and then after that it will become a curve, right. So it's going to reduce. Then we also talked about launching of a satellite. How is a satellite launched? We can't just throw up a body, and just expect it to orbit Earth, right. So we have to send it at a height, and then also simultaneously it has to catch the orbit, right. The orbital speed must be proper, desired speed must be achieved, right. So we talked about the different trajectories which are possible. If the satellite is not thrown with the right speed, then what can happen? It may crash to Earth using an elliptical path, or it may even go in an elliptical orbit, or it may escape the Earth's gravitational field using a parabolic or a hyperbolic path. Okay, so that gives us the concept of critical speed and escape speed, right. So critical speed is that speed with which we should release the satellite so that it goes in a circular orbit. Okay, and escape speed is that speed, right, if the satellite gets the escape speed, then it's going to escape the Earth's influence. Okay, so these are the topics we talked about last time. So today we need to discuss, once the satellite is launched, okay, so once the satellite is in the orbit, what happens after that? The basic idea here is, do we need fuel? Okay, is fuel required to go in a circular orbit or elliptical orbit, whatever is the orbit? Does the satellite need fuel to go around Earth? Okay, so think about it. So let's talk about a satellite of Earth which is the oldest. So can you guess which is the oldest satellite for Earth? Right, the very first satellite which Earth had. So it is not a satellite that we have launched. Okay, it is nothing but our moon. The moon is a natural satellite for Earth. So if the moon is a natural satellite of Earth, think about it. The moon is orbiting Earth just like a satellite would. Then does the moon need any fuel to go around Earth? Right? The answer is no. The moon does not require any fuel to go around Earth. Okay. So similarly, all our satellites also, they don't need any fuel. No fuel is required for the satellite to go in an orbit around Earth. So then how is it happening? Okay. Why, since time immemorial, the moon is orbiting Earth, and why once the satellite is launched, right, it doesn't need any fuel to go in an orbit. Okay, some fuel is still stored in the satellite, but it's not needed to go in a circular orbit. So the reason is centripetal force. Okay, centripetal force. So let's understand this idea. What is centripetal force? So you can see this is a giant Ferris wheel. Okay, and you can see it's going in a circle. Okay, each seat, you can say, if you're sitting on that Ferris wheel, and each seat is doing circular motion. So whenever a body does circular motion, please note, centripetal force is a necessity. If you want to continue living after the next 1 minute, you want to be alive, what do you need? You need oxygen. Oxygen is a necessity, immediate necessity for the human body. Okay. Similarly, centripetal force, our body may still exist for 1 minute, maybe about, we can hold our breath for 1 minute. So you may say, okay, my body is still surviving without oxygen for 1 minute. But circular motion, right, any body going in a circle will not survive even for a split second without this force, centripetal force. It is a force towards the center of Earth. So each seat here, you see there is a connection to the center of the wheel, of the Ferris wheel, where that letter W is written, right? This every seat you see has a connection. These lights are there just to, just for show, but basically The idea here is, at least using these lights you can understand there is a connection with the center. So the same thing, the exact same thing is happening even for all the planets going around the sun, or if you talk about the satellites going around Earth, right? So we have all, this is our solar system, right? So this is the sun, that's Earth right there, and that's the moon of Earth, okay, and then all the other planets are there. So as they are going around the sun in circular orbits, okay, there is a centripetal force, there is an invisible link. In the Ferris wheel you could see the connection to the center, right? The metal rods or the metal structure was providing a force, a connection to the center. So here also all these planets are invisibly, we will not be able to see it, but they are invisibly connected to the sun, the center of the sun. Any planet you consider, right? If I consider this planet, so to the sun, from the center of this planet to the center of the sun, there is an invisible connection, there is an invisible force. Why invisible? Because it's not like the Ferris wheel where there is a metal rod and a connection, direct connection which we can see with our eyes. Okay, it's not that kind of a connection. It is a connection with a force. And which force is that? It is the gravitational force which was given by Newton's law of gravitation. Okay, so that is the necessary centripetal force. Somebody has to give this centripetal force. If the centripetal force is not there, circular motion cannot exist. No planet can go around the sun, no satellite will be able to go around Earth. Okay, so that is the reason. So once this centripetal force is provided, that's it. The planet will keep on going around the sun, the satellites will keep on going around Earth, the moon will keep on going around Earth. Okay, so once the motion is established, it will continue forever. Why? Because gravitational force is existing forever. Okay, so that is the reason why, right, we don't need any fuel. Then what is the fuel required for then? If satellites do store some fuel, it's basically to change their orbits if required. Okay, at a certain stage during their lifetime, if there is a maneuver needed to change their orbit, to change their height, then some fuel may need to be used, right, to do that. Okay, so this should give rise to a question in your mind that if all these satellites, the moon around Earth and all the other satellites, they keep on revolving till eternity, then what happens to them? Do they just keep on running forever? So you need to understand, satellite is an electronic equipment. It's a very fancy, expensive, okay, very scientifically advanced, but at the end of the day it's a machine, and machines have a lifetime. So its electronic circuits may stop communicating with Earth maybe after 10-15 years. Okay, they will usually have a lifespan of around 10 to 15 years. So for 15 years or so they will communicate information to Earth. After that they will stop working, but they are still going to stay in orbit. They are not going to stop revolving around Earth. Okay, they are not going to stop orbiting Earth. They stay there in orbit forever. Okay, so what is going to happen because of this? As a result, we have a lot of objects in orbit. Okay, and this table is giving you a rough idea as to how many objects are there around Earth, right, in space. So this data is from Wikipedia and it's as of January 2019. Okay, objects which are smaller than 1 centimeter in size, there are 1.28 crore, approximately 1.28 crore such objects. Okay, objects which are between 1 and 10 centimeters, around 9 lakh of them, and objects which are bigger than 10 centimeters, okay, about 34,000 of them. So the first question that should arise in your mind looking at this table is, how can we have an object which is less than 1 centimeter, okay, or maybe 1 to 10 centimeters, more than 10 centimeters. Yeah, it does make sense. Satellites are big, what to speak of 10 centimeters, there may be several meters. Then what about these objects which are less than 1 centimeter? So please understand, everything on the satellite, even the paint on it. So when the satellite is launched using a rocket, So the rocket took it to some height. In the process, the paint which was covering the rocket, it may be scraped off and it may stay in orbit. So you can really have very tiny, even microscopic objects which are actually in orbit around Earth. And all of these things, right, form what we call as space debris, right? Basically, kachra in space. Okay. So you may say, okay, fine, it's in space, it's not polluting the atmosphere or anything in Earth, on Earth, right? Inside the Earth's atmosphere or on the surface of Earth, it's not causing any pollution. So what is the problem? So if you want to know what's the problem, please watch the movie Gravity. Okay, if you have not yet seen the movie Gravity, you better watch this movie to understand what problems, okay, what havoc, I would say, space debris can create. Okay, so just to give you some idea, this is a simulation of different particles which are orbiting Earth. Some of them may be satellites. Each white dot here is some space junk. Okay, obviously the size has been exaggerated to show its position. If the Earth has been shown as such a tiny sphere, okay, then these particles would not be even visible if I want to show the diagram to scale. Okay, so these sizes of these particles have been exaggerated, but this just gives you a rough idea as to how much junk is orbiting Earth. Okay, and as you can see, there are two major orbits here. One orbit is very close to the surface of Earth, okay, just outside the Earth's atmosphere, and this is the Leo satellite orbits. Okay, and this one here, this one big circle here, is what is called as a geostationary satellite, or it's the geosynchronous orbit. Okay, we'll talk more about it in future lectures. So that's where major, most of our satellites are existing. And what problems can they cause? Okay, just a sample again. This is the window of one of the space shuttles which was damaged because of some debris hitting, right? And just imagine if that window would have cracked, okay, what could have happened? This is a big hole which was created in one of the other satellites, okay, again by space debris. So this is one of Russia's satellites, okay, Mir satellite. And this area, these are the solar panels, and this area here, this square area, the yellow square, you can see. So that area has been magnified, and you can see it has these high contrast spaces here, these black dots. Okay, several black dots are there. I'll just highlight them. So all of these dots actually are damages which have been created by space debris. Okay, so that's the idea here, that okay, these things they can cause a lot of problem. All right, so the next topic we are discussing today is time period of a satellite. Okay, so why is this important? If you have seen the movie, you must remember that the astronauts there, they have been told, right, to set their stopwatch to 90 minutes. Okay, because they are expecting the debris to hit them again after 90 minutes. So how did they get this number? Okay, 90 minutes. So actually, if you just check it on Google, approximately 92 minutes is the time period of ISS, the International Space Station that is orbiting Earth. Okay, it has a time period of about 92 minutes, so that's roughly around 1.5 hours. Okay, so that's how they got this time. So not just for that, but even otherwise, time period of a satellite is an important information needed for the scientists, and companies that are launching these satellites. Why? Because satellites are communicating with Earth. So if a given satellite, suppose it is sending some information which is being received by some antenna, some dish antenna on the surface of Earth, then in a few seconds that satellite is going to go away, because it is orbiting Earth, it's going to go somewhere else. So the time period will help us know after how much time will that satellite be back into the same position. Or in other words, if I know the time period, I will know how many satellites I would need in the orbit. Okay, one satellite is not enough. We always, satellites usually, especially for communication purposes, they are launched in a set. There will be several satellites orbiting in the same orbit. Okay, so how many satellites would be needed so that there is non-stop communication possible with Earth? Okay, so that's why this time period is needed. So it's can be found out very easily. Time period, the formula, we can just use time is equal to distance upon speed. Okay, and the distance in the orbit is 2 pi r, right? So circular orbit, so the circumference 2 pi r, and the speed with which it is going around the Earth in a circular orbit is vc, the critical velocity. We know that, right? So if I just substitute the formula for vc, right, which we saw in the previous lecture, if we just substitute that, we are going to get the formula for time period as 2 pi square root of r cube divided by gm. Okay, so again it's t is equal to 2 pi under root r cube, small r cube divided by gm. This small r, please note, it is equal to capital R plus h. Okay, small r throughout the chapter is capital R plus h. So if I square, right, because there is a square root here, if I square both the sides, right, we will get in the LHS t square. Now in the RHS, if you notice, 2 pi is a constant, capital G acceleration, the universal gravitational constant, and capital M, which is the mass of Earth. These are constants, right? 2 pi, G and M are constants. So if I just get rid of all the constants, then I can say t square is proportional to r cube. This is a very important formula, t square proportional to r cube. We will have lots of MCQs related to this formula. Okay, so time period of a satellite, t square proportional to r cube, or you can say t is equal to 2 pi square root of r cube by gm. Okay, all right, so let's solve some numericals. So the first one is your textbook question number 4. Question 4 are all numericals. Within that, the fourth one. Okay, two satellites A and B, they are revolving around a planet. Their periods of revolution, that means their time periods, are 1 hour and 8 hours respectively. So what should we note? Okay, so please remember data diagram equation. Don't continue reading unless you have written what you have read. So I can say TA is 1 hour, TB is 8 hours, because they said 1 hour and 8 hours respectively for A and B. Okay, so continue reading. They are saying the radius of orbit of satellite B is 4 into 10 raised to 4 kilometers, and they are asking us find the radius of A. So RB is given to us, the radius of the orbit. Okay, it's not the height, it is straight away the value of small r which has been given to us, 4 into 10 raised to 4 kilometers. Okay, that's a very large height. Okay, so how do we get the value of RA now? Very simple. We know the formula, t square is proportional to r cube, but what I want here is r. I don't want r cube. Okay, I want to find out RA. So let us take cube root on both the sides. Cube root, just like square root, we can take cube root, right? Raised to 1 by 3. So what will we get? If we take cube root of r cube, I'm going to get r raised to 3 raised to 1 by 3. So the 3 will get cancelled off. I'll get r raised to 1. But the t square will become t raised to 2 by 3. T square again raised to 1 by 3. So 2 into 1 by 3 will become 2 by 3. So t raised to 2 by 3 is proportional to r, or in other words, the radius is proportional to t raised to 2 by 3. So now I can just understand it's a ratio question. So just take a ratio, right? RA by RB will be TA by TB the whole raised to 2 by 3. Okay, and we know the numbers for TA and TB. Let's just substitute them. So I can take RB from the denominator here, right? RB was a denominator. Take it in the numerator and put the values of TA and TB and RB. So RB, the value is 4 into 10 raised to 4, right? We have noted that down, kilometers. And TA is 1, TB is 8. So 1 by 8. Now what is the cube root of 1 by 8? The cube root of 1 by 8 is 1 by 2. Cube root of 1 is 1 and the cube root of 8 is 2. So this 8 has become 2 in the denominator, and I've already taken the cube root, so the square still remains. So I have now 1 by 2 square. And what is 1 by 2 square? It's 1 by 4. So that 4 and this 4 will get cancelled off, and all I'll be left with is basically 1 into 10 raised to 4 kilometers. Okay, so that's the answer for the fourth one. One last numerical we will take is again textbook question number 4, the seventh one in it. Okay, calculate the speed of a satellite in an orbit at a height of 1000 kilometers. So please note here, the height is given, not the radius of the orbit. The height from the surface of Earth is 1000 kilometers. Now kilo itself, this K, kilo means 10 raised to 3, and there are 3 more zeros here. So 10 raised to 3 plus 3 will become 10 raised to 6 meters. Okay, in meters, meters is the SI unit. Okay, so we need to find out the speed. So the other constants have been given to us. Okay, this is the textbook question, so they are giving us the constant. Usually they don't give us such constants in the exam, especially in the entrance exam. Okay, so you need to memorize these numbers. ME has been given to us as 5.98. We can round it off to 6 as well in the MCQs, but right now we'll take it as 5.98 into 10 raised to 24 kg. And capital R is the radius of Earth, which is 6400 kilometers, which can be written as 6.4 into 10 raised to 6 meters. Okay, so again, this is a very simple substitution question, right? We just need to know the formula and get the answer. Plug in the numbers and get the answer. Okay, so the formula for VC, we know critical velocity, right? They want speed. So that's the critical speed of the satellite. It's going to be square root of gm by r, right? Gm by small r, and that m here, right? The suffix e has been put because it is nothing but the mass of Earth. Okay, so gme by r, or if you want, you can replace small r with capital R plus h. Okay, so that's it. Just plug in the numbers. The value of G, capital G, right? Universal gravitational constant, it's 6.673 into 10 raised to minus 11. Then mass of Earth is 5.98 10 raised to 24 divided by capital R and H. Both have been written here in the given. So we can write capital R is 6.4 10 raised to 6 and small h is nothing but 10 raised to 6. So now I can gather all the powers of 10. So in the denominator, first of all, if I take 10 raised to 6 common, I'll get 6.4 plus 1. So that will become 7.4 in the denominator. Then 10 raised to 6, which was taken common, it goes in the numerator and becomes minus 6. And I'll just write 24 and minus 11 together. So I have 10 raised to 24, minus 11 and minus 6, and all the numbers as it is 6.673 and 5.98. So again, this can be simplified as 24 minus 11 minus 6 will give me 10 raised to 7. But since I want to take square root, I can't easily take the square root of 10 raised to 7, but I can very easily take the square root of 10 raised to 6. Okay, so let's write it as 10 into 10 raised to 6, and that 10 when multiplied to 5.98 becomes 59.8. Okay, so now the square root of 10 raised to 6 is simply 10 raised to 3, and the remaining part, please pause the video here. Okay, and you can use your log books, log and anti-log calculation, and solve it to get the answer. Critical velocity of the satellite is 7.343 into 10 raised to 3 meters per second. Okay, so that's all for today. See you in the next class.